I run a design computation consultancy named Research Lab in India, and as the name suggests, we render design computation services to architectural practices in India and also across Southeast Asia. Along with that, we time and again have been releasing Grasshopper plugins, which have been used and help the community of designers. One of the plugins is called Chingri. Basically makes Mondrian-like 3D forms and 2D compositions, which can then be further developed in the design process. The other one, which is of particular interest to the AEC industry, is a plugin named Elish, which basically takes an orthogonal plan as an input and places columns and beams on the plans depending on the values of minimum and maximum allowed slabs. So the variables are A, the floor plan, and B and C, the minimum and maximum allowed floor slab. So one doesn't need to keep repeating the soft if-else logic that one executes in the mind when one lays out columns and beams on regular run-of-the-mill orthogonal designs. Along with that, I have been visiting faculty in 2 institutes in India, namely School of Planning and Architecture in Delhi and CEP University in Ahmedabad. This introductory presentation would be discussing the differences between AI, machine learning, and neural networks. And then we're going to cover key concepts of the various kinds of learning algorithms or various kinds of algorithms in machine learning. And then, of course, we're going to discuss about supervised learning, which is the specific learning that we're going to use to execute our tasks. And lastly, I'm going to briefly discuss about how neural networks actually work. What are the various functions that work behind it? How does data get propagated forward, and how does it get propagated backward, etc., etc. Right. If we begin with the idea of machine learning, the major difference compared to traditional programming, and when I say traditional programming, as the diagram shows, I mean that we know the rules of the algorithm and we have input data. So we combine those two, and those two yield us the answers or the output. For example, take any mathematical function. If, let's say, we're talking about x plus y equal to z, so in the traditional programming domain, the algorithm we know, which is addition of 2 inputs, and the answer is collected or computed based on the algorithm. The main difference with machine learning is that in machine learning, we do not know the rules, or we do not know the algorithm. We have a bunch of input data and correspondingly same number of output data, and we have no idea what is the logic or the rationale that transforms the input data into the output data. And so we use machine learning to, in a way, generate the rules so that later on, with new set of input data, similar output data can be mapped or projected. So again, just to revise, in traditional programming, the algorithm and the input they are known, whereas in machine learning, the algorithm is not known. We have input and output, and accordingly, the algorithm is appropriated using either neural network or other kinds of machine learning techniques. This has been a doubt or a fuzzy area for a lot of us, wherein what is the difference between artificial intelligence, machine learning, and neural networks, right? In a way, as the diagram suggests, they are similar or related to each other. Neural network happens to be a specific kind of machine learning, and machine learning happens to be a specific kind of artificial intelligence. Artificial intelligence basically would include any program or code or algorithm which is capable of solving tasks that require some sort of human intelligence. But where it is different from machine learning is in the fact that it need not be using only input and output data to map the algorithm. It can be a traditional programming as well, where humans or the coder defines the rules. A typical example of AI, which is not machine learning or neural network, is the very basic rudimentary chatbots that we see on certain websites, where you log in and then you see options. Would you like to speak to the customer care? Which product do you want to chat about, etc., etc. So there are a bunch of questions which are kind of correlated to each other in a hierarchical if-else network, and then we navigate through it. So the programming in the back end is pretty straightforward using if-else and human-defined rules. However, the task that it does is kind of mimicking an operator, which is why it's categorized as AI. Machine learning, as we saw in the previous slide, this one, is basically an example of AI where the rules are not known and the machine needs to learn to predict the new answers. Not all machine learning algorithms use neural network. Typical examples of machine learning would be regression analysis and KNN analysis. I'll talk about them in the next slide. And neural networks are, of course, specific, highly advanced machine learning algorithms that use a series of interconnected neurons, which are essentially just mathematical functions. We like to call it neural network because it abstracts the connection of neurons, but it's not quite literally the same, of course. It's basically a bunch of functions connected to each other. And of course, similar to machine learning, or rather, because it is also machine learning, a specific kind, it learns to solve a task by mapping the input to the output. Of course, it solves much more complex problems than machine learning, which doesn't use neural networks, some of which would be stock prediction, or in terms of betting, which would be score prediction of matches of different sports, and of course other services like suggestion of music on Spotify, or suggestion of products on Amazon, etc., etc. Just a couple of examples of machine learning algorithms that do not use neural network. That one is regression, which basically estimates the relationship between an output, which is also known as the dependent variable, and one or more inputs, which are known as independent variables. Two of the most commonly used examples of regression are linear regression and logistical regression. These jobs can also be taken care by neural networks. So the question becomes, why do we use neural networks if these can be done using regular machine learning algorithms as well? The answer is in the accuracy of the model, or in the accuracy of the prediction. Neural networks happen to be significantly more accurate than the regular linear and logistical regression algorithms in finding a relationship between inputs and output, or multiple outputs. Another example, which is called the KNN classifier, is basically used to classify different objects. When we browse Netflix or any other streaming device, you must have noticed that a bunch of suggestions are categorized into different types. But the categorization doesn't remain the same from one user to the other. KNN would be a very rudimentary method of getting that done. It's actually done using neural network, but the concept, if it is to be done using machine learning, which is not using NN, rather neural network, would be using KNN, which basically, if you see the example here, if there are a bunch of, let's say, orange data points and a bunch of green data points, and let's say a new series is added into Netflix, the question is, between the two categories, where does the new series get categorized? What KNN does is it literally calculates the distance to all the green dots and the distance to all the orange dots, and then compares to which cluster it is literally closer to in terms of distance, and then it gets categorized in that particular category. Now, of course, this has a variety of limitations where more complicated inputs like browsing history or preferences or watching time or which actors one likes to watch, and those complicated inputs cannot be incorporated when we use KNN, because it literally uses distance in the XY plane or the XYZ plane to categorize different inputs. So which is why, again, when you use neural network, not only are the inputs numerical, but inputs can also be images and timestamps, and of course audio as well as video. So clustering or classification becomes much more sophisticated and much more accurate when we employ neural network instead of something like KNN. Sorry. All right, now let's talk about the three kinds of neural network learning algorithms. These are also applicable for any machine learning algorithms as well. There are three of these, one being supervised learning, which is the one we are going to use. The second is unsupervised learning, and the third is reinforcement learning. In the first one, we begin, all of them use some version of input data and output data. Let me first concentrate on the first two kinds. The only difference between supervised learning and unsupervised learning, as the name suggests, supervised versus unsupervised. In supervised learning, the input data have labels, or in other words, the input data tells the algorithm what particular object it is, or what is the data type. And in unsupervised learning, that label or the column header is missing. The algorithm is not told what kind of data is being fed. So what is the difference? The difference being, in supervised learning, for example, if we train a neural network on a variety of images of cats and dogs, eventually with enough number of iterations, the algorithm will learn to differentiate between dogs and cats given a new image is used as an input. Just give me a second. Someone from CAADRIA has emailed me. Right. So the input data, let's say there are 100 images of cats and 100 images of dogs. So while training the neural network, all of the images which are images of cats would be labeled cats, and all of the images which have input data which represent dogs will be labeled as dogs. Or in other words, label is the term used for the output, because when we enter new images, the machine is supposed to tell us, is it either a dog or a cat, right? So the label, in other words, becomes the output. So with each input set, the output needs to be assigned. In unsupervised learning, that is not the case. The output or the label is not given by default. So if we feed a bunch of images again of cats and dogs into an unsupervised learning algorithm, what are the different things we can do? What we can do is we can tell the algorithm to classify all the input images into, let's say, 2 types. It will automatically learn the features and intuitively divide it into 2 parts, where one will be cat, the other would be dog. However, because there are no labels, the algorithm will not know that A is dog and B is cat. However, those 2 will be divided. So why do we use 2 different types? Because in unsupervised learning, instead of saying divide the data into 2 parts, if we, let's say, specify divide the data into 4 parts, then 4 groups would be formed. Possibly, apart from dogs and cats, there could be one group of images which would be something in between, wherein it's not clear if the image has a dog or a cat. And the 4th category could be images which do not have a dog or a cat. So basically, the more number of divisions you specify the machine to have, it divides the input data in those many, of course, in those many divisions, and accordingly, we as users have to decide what is the suitability or the use of such an algorithm. So in label data, in supervised learning, because there would be only 2 labels in this example, dog and cat, there cannot be any 3rd output type. Whereas in unsupervised learning, how many types of classifications we want, we can specify, and accordingly, it will be divided. Another example would be, let's say, classifying songs from a playlist. If we say divided into 2 parts, it will divide the audio files into, of course, 2 parts, probably depending on the tempo of the music or the bit rate, or if the neural network is far more complex, then it can also map things like mood and emotion of the audio files, and it'll divide it into 2 parts. If you mention 3, then it'll divide it into 3 different kinds of music types, and then if, let's say, we specify 10 types, then probably we'll start seeing the various genres of music being classified from the playlist. Reinforcement learning is completely different from both of these. Doesn't really use data in the traditional sense. What we do in reinforcement learning is that we gamify a problem, wherein we define an environment where, let's say, there are obstacles, and there's a place to reach or an objective to perform, and there's an agent who needs to maneuver through the environment to not get caught up in the obstacles, and B, complete the given task, be it traveling from point A to point B while not being caught up in the obstacles, or traveling from point A to point B in the fastest manner possible, or performing any other specified task. Now, how does the agent do that? Are we going to explicitly code? Of course not. The agent does that by a reward system, Whereas, let's say, if the agent has to move inside a maze, and each time it goes away from the exit point, it gets deducted points, and at each step, if it automatically goes towards the end point, it gets added a positive reward, and then it, through various iterations, it learns how to navigate through the maze. I'll talk about reinforcement learning in a little more detail later. As this image clearly specifies what I was talking about, supervised learning can, of course, be used for calculating output values which are numerical in nature, which we're going to do, wherein, let's say, there are a bunch of input data and some sort of output is being calculated from it. The other is classification, which again I talked about, which is, let's say, into cats and dogs, or in terms of numbers, let's say in the world of medicine. An example of classification within supervised learning would be, given, let's say, the age, gender, comorbidities, condition of, let's say, heart, lungs, etc., how vulnerable is a human to serious infection if he or she is infected with the coronavirus. That would be an example of classification. Let's say there could be 3 classifications: severe, moderate, mild. And I mean, we know how it works, so you can guess the rest. And unsupervised learning, as I mentioned, it calculates associations between various input data types, like the example of music I spoke about, and also it clusters various data input into, of course, different clusters. An example of this, an example of association would be when we browse products in Amazon. You'll notice that towards the bottom of the screen, we get more suggestions of similar products. Those are suggested using an associated unsupervised learning algorithm, which keeps on going in the backend. And it's not just that. Something else also happens, which is clustering, which is it keeps track of our browsing history, and then depending on which object we have been browsing, you'll notice that randomly a couple of those also pop up. So that happens through clustering, wherein it maps the various clusters we've gone through previously, and it suggests that in the prompt as well. As far as reinforcement learning is concerned, like I discussed, the agent, let's say, as the image suggests, starts from top left and has to make its way through the maze to the bottom right, and it's given a reward function where, let's say, if it takes the right path and goes closer to the exit, then it gets a positive reward. If it goes inside and gets caught up here, then it gets a negative reward. And the moment it gets caught up here, the process starts again, and it gets repeated again and again and again. And through that deterministic process of failing and learning and failing and learning again and again and again, quite literally how kids learn to perform various tasks, which is to fail again and again and again and then succeed. It kind of mimics that process. And yeah, to summarize, in supervised learning, we have input variables and output variables, where the input variables are called independent variables. They're also called features of the output, and the output is basically called dependent variables or labels. And of course, both of those are fed into the neural network, and the neural network itself iterates through uh, the data to make sure that the output that it's giving has the least amount of error or deviation that is possible within those many number of iterations. Unsupervised learning has no labeled input, or in other words, has no specific output in the data that is fed into the machine, into the neural network algorithm, and it basically it performs tasks which typically explore patterns and trends. And in reinforcement learning, there's an agent which has to make its way through the environment, and there are reward systems to assist its decision making and learning process. Of course, like I've discussed, supervised learning can be used to predict numerical values and forecast sales, etc. And unsupervised learning uses clustering and associations. And because it is good at determining associations, accordingly, it is also good at determining disassociations. So it can be used to detect outlier data in data points in a large data repository, which is basically something that is used by the security forces to check for messages or posts which could lead to law and order issues, or also by the various social media companies to detect which posts or which words sort of stick out like a sore thumb, do not go with the policies, and then they flag the posts. As far as reinforcement learning is concerned, the biggest example or the most relevant example is how self-driving cars are being made, wherein the algorithm inside the self-driving car uses a system of reward and after seeing the environment, and then it sort of makes its way through the proverbial maze, which in this case would be the real world, and of course solving various kinds of games. I'll share a video. Before Tesla came into the picture and self-driving cars became a reality, the most significant jump or contribution in terms of reinforcement learning or the use of neural network was a game of Go between AlphaGo, which was a reinforcement learning algorithm developed by Google DeepMind, and Lee Sedol, who was the champion of the game Go at the time. Some of you may remember that in the late 90s, there was news that a computer had defeated the world chess champion at the time, and there was a lot of speculation as to how or where the course of computation will go from that point on. The difference between that event and this event would be chess mathematically has a significantly less number of move sets or less number of possibilities compared to Go. In fact, the number of possibilities within chess is so low that, in terms of computation, of course, is so low that any machine these days, even my laptop or your laptop, is capable of literally going through all the possibilities through brute force and determining which would be the best possible outcome with respect to the situation of the game. And that is exactly what was done at the time, wherein the machine used brute force to go through all the various options and then predicted which move would be the best. So of course, with that in mind, brute force of computation, the human mind cannot really compete with that, because we are quite simply not capable of calculating in that speed or in that volume, of course. Keep in mind that in a game of Go, the number of possibilities is in fact higher than the total number of atoms present in the universe, which basically means that there is no computer. And I say that responsibly, there is no computer in the universe which is capable of computing those many possibilities and performing or deciding which move to play next. So instead, there was a paradigm shift, wherein instead of using brute force, which was the case in the game of chess, in the game of Go, reinforcement learning was used, wherein, of course, the environment was the game of Go. The reward was the rules of the game, which were the rewards came from the rules of the game, which included that when you surround your opponent's pebbles, then your opponent can't go further, and then there are various other intricate rules. You can look up those later on. So basically, the reinforcement learning algorithm in this case went through hours and hours of simulation to learn how to play the game. Mind you, learn how to play the game in this case would mean to understand the patterns and the trends in which better moves can be made instead of using brute force. So it's kind of mimicking human intelligence, so to speak, instead of relying on computational power. And as it happened, AlphaGo had indeed defeated Lee Sedol. And that's not the complete takeaway. There was a move, and most possibly the second last game in the series, where the computer played a move which seemed absurd and meaningless to not only Lee Sedol, but also the commentators and the spectators who were watching the game. But only later on, 10, 20 steps later, it became obvious why the system had played that move. And so again, at the end of the game, as you can see in the quote at the end, Lee Sedol was in awe and sort of accepted that he's never seen a human play that particular move. So because it's trained to find patterns and then get rewarded, etc., and it has no bias, so to speak, it can be ruthless in discarding what it has learned so far to learn something new, which we have an inherent internal friction within us to do that. The machine can learn new patterns, learn new techniques, which would be rather surprising or unconventional to the human brain. I'll share a video. This is a very rudimentary example of reinforcement learning, where the typical game of snake is being learned by reinforcement learning. And if I go back, so the environment is, of course, the box within which it has to move. And the head looks in these directions and decides in which direction to move. Of course, the direction is restricted by the 4 x and y axis directions. And of course, it also calculates the distance of its head to the position of food, and of course, also the distance to the wall. And lastly, distance to itself. and then it decides in which direction it needs to go. So as you can see, in the first few rounds, because someone sent a message. Right, yeah, I'll get to that. Right, so in the first few generations, because the reward function, even though the reward function says that if you crash into the wall, you get deducted points, or if you sort of crash into yourself, you get deducted points, because it hasn't gone through those many iterations and it begins from, let's say, by being blind, it makes a lot of mistakes and it learns from those mistakes to then eventually add priority to which state, be it going forward or not intersecting with itself or not intersecting with the wall, which state needs to be given more precedence or more weightage as it goes through different generations. Like, for example, here in this case, it avoids the wall pretty much fine, but it starts to intersect with itself. And at this stage where you were seeing that it's kind of going in the same direction and again in the loop, it had internalized the reward of not intersecting with itself with the highest weightage, which is why it's not going towards this and instead sort of moving around the same loop. Anyway, so this process is repeated again and again and again, and of course, as you can see, as the number of generations increase, and this is only in the 21st generation, mind you, or in the 21st trial, it becomes quite adept at playing this particular game. Now, genetic algorithm in this case would be used to reject or filter out the weightages it gives to different reward functions. Like I mentioned, you get a positive point if you avoid colliding into yourself, get a positive point if you go a step towards the food. You get a negative point if you, of course, collide with yourself. You get a negative point if you collide with the wall, and you get a negative point if you go away from the food. So there are 5 different factors. There could be a 6th or the 7th, which probably I'm not aware of if that is the case, but evidently, as an example, let's say these are the 5 rewards, 2 positive and 3 negative. And there are different weightages assigned to it, right? Which basically lets the snake decide which direction it has to move to. And genetic algorithm is used to optimize those weights while it learns through various generations. If you have used GA, you would know that it sort of goes through different generations to optimize that value. So that's basically, so in a way, it's an interaction between the environment, the agent, which in this case is the snake, and the reward functions, wherein the reward functions or in other words, the weightages which are given to the reward functions are optimized using genetic algorithm within the larger domain of reinforcement learning. Right. Coming back to the example of self-driving cars, I think this would be pretty obvious to you by now. The environment or the state would be basically the position of pedestrians or vehicles or signages or the condition of road. Action would be, of course, number 1, controlling the speed, and number 2, controlling the direction. And rewards would be to be safe and comfortable and be efficient and avoid collisions or going above speed limit, etc., etc. So through a combination of these, and of course with very sophisticated tracking systems to, first of all, get the data of the driving environment, and B, decipher what that actually means in terms of coding. So, and then go through action and reward, etc., etc. That's basically how self-driving cars work. Now let's talk about supervised learning specific to design, or in specific to our workshop. Till now, supervised learning has been used for of course, classification of images. So let's say there are, of course, various orders of arches and columns, right? So you can train a neural network to identify if a column is Ionic or Doric or Corinthian or any other type, given that you've trained the neural network with a bunch of images of each type. The other that it is used for is to, of course, map a bunch of input data onto an output data, which would be numbers, which is basically used to quantify subjective feeling or subjective opinion, some of which could be how the environment is visually perceived, which is not only restricted to the debate of originality or plagiarism, but also goes beyond into the perception of urban safety, the perception of beauty in a streetscape, and so on and so forth. Any subjective opinion that you can think of can be mapped and predicted using supervised learning. It is best advised to be used for cases which cannot be simulated or calculated, because the moment you can simulate or calculate something, it sort of becomes a traditional programming type, and it's advised not to use any of these. So what we are going to do is, of course, tomorrow and the day after, because today we're going to explore Google Colab using the 2 Excel sheets that I've already shared. What we are going to do later on is that we're going to work with a parametric script of the absolute tower, which is designed by Mad Architects, and we're going to vary the main design. The variations are called design variants, and then use crowdsourced data to train a neural network to then later on predict how plagiarized or how original a new design variant is perceived to be. So, I mean, the definition is already made. I'll share it with you, because of course the focus of the workshop is not developing parametric scripts. So basically uses 12 different variables. Let's say the size of the ellipse of the floor plates, which would basically mean 2 variables, radius 1 and radius 2. And then just to add more visual diversity, we added variables which would make the ellipse more rectangle-like, and then B, add indents at the midpoint of the ellipse or the rectangle, so you start up getting star-like shapes. Of course, controls of scaling towards the top and scaling at the bottom, and the most obvious, which is the total rotation in the flow plates, and 4 more values to control the nature or the slope of the rotation. Is it uniformly rotated? Is it rotated in a Bezier curve? If it is a Bezier curve, then is it top heavy or bottom heavy or mid heavy, so on and so forth. And lastly, Since the design has balconies, we've also added a Boolean toggle to switch off the balconies and sort of make the exterior look like a completely glass tower. So what is the procedure of doing this? We generate a bunch of options, right? And the variables that make those design variants or options are of course called features, and we tabulate them, and then the corresponding images are shown to, let's say, a crowd group, which in our case would be us. And for each of the options, we are going to give it a score between, let's say, 0 and 1, where 0 would mean it's completely plagiarized and 1 would mean it's original. And let's say there are 14 of us, each one will give his or her opinion, and then later on it will be averaged out. So each option will have an originality score, and this output, this originality score, is the label, which is why it's called supervised learning, where the variables of the design variants, plan, radius 1, radius 2, corner point, midpoint, total rotation, the 4 variables to control the nature of rotation, the state of the balcony, and scale top and scale bottom. These 12, the features are fed along with the originality score, which is the label. So how does the neural network get trained? As of course a list of the variables, which are the features, and the evaluation score, which is the label, and then both are fed into the neural network, and then it maps one to the other. And then once the learning is done, then we can vary our features or variables, and with each new option the neural network can tell us what is the predicted originality or plagiarism score. In other words, if, let's say, from within all the solution domains, we pick only, or rather we review through the crowd, or if the crowdsourced data has only, let's say, 7 or 8 of the magenta dots, what machine learning can do for us, or neural network can do for us, is that it can appropriate the solution space depending on the number of data points we have. So we no longer need to sort of go through all the possible design options, which kind of typically happens in the case of genetic algorithm, where all the input types are distributed across the solution space, and gradually it goes towards picking the optimized solution. That is not what's happening here. Here we let's say have the answer, which in this case is the originality estimate for a very selected or very few design variants, and the rest of it is approximated by the neural network through the process of training. So as the slide says, it approximates all the possibilities based on only a few evaluated options. And of course, this we've already done the study and quantified the difference of visual perception of originality between architects and non-architects. If you compare the two images here, you notice that, let's say, in the second last row, most of the options are green, whereas in the case of non-architects, most of the options are yellow to yellowish green, which basically means that if you look at the legend at the bottom, non-architects tend to be more doubtful about the originality of an option, or in other words, architects tend to be more lenient in categorizing a design variant as original or as far away from being plagiarized, which of course through various means, which we're going to cover in the last day of the workshop, we can quantify and generate graphs to sort of communicate that idea. So we'll get go through these slides again in detail when we sort of dig into this particular exercise. The question is, what other kinds of solutions can be made or can be simulated using this? This is one particular project that we are working on right now, which sort of leverages the algorithm developed by self-driving car companies, which basically segments an image or a video into its constituent parts, be it buildings, signages, cars, pedestrians, sidewalk, trees, etc. So we're using this algorithm in collaboration with an app which has GPS tagged safety score as perceived by women in various cities in India. And so we're using a combination of these two to assist urban designers to predict the safety perception of various parts of the neighborhood design that they may do. Keep in mind, because for each spot for that given score, and the spot will have a certain distribution of cars and building blocks, sky, number of pedestrians, and signages, and trees, or other such elements. Because with each different score, those values vary. What it means is, for a given neighborhood design, because each spot will have a different quantity of those elements, the safety score will vary within a neighborhood. And not only that, because it's GPS tagged, we can sort of map the difference in perception of urban safety from one city to the other. So not only will different spots have different values, but also the same design, when taken from when moved from one city to the other, will yield a different safety score. So in this case, the features would be, I think I should pause for a bit because of the disturbance. Right, it's gone. Yeah. In this case, the features would be the percentage of area dedicated to different, let's say, types of objects. So people will be, let's say, 0.05, cars would be 0.2, sky would be 0.25, so on and so forth. And also the mutual distances between their center points. So in other words, if people are towards the top of the image, it would mean that probably they are not directly accessible, which would mean that the street is desolate. So though if people are towards the top of the image, it will basically mean that they are at a distance. So the center point of the different segments are also to be calculated. So those become the feature, and the label becomes this safety score, and then the neural network goes through those iterations and learns how to predict. Right. And so what would be the implication of this in the larger context of the business of architecture or design. In my opinion, the biggest contribution of such techniques would be establishing a clearer communication or understanding between the client and the designer or the architect about the client's aesthetic sensibility. Many a times when you start designing projects, understanding the client's preferences itself takes a bunch of meetings. And so in those meetings, more often than not, you're trying to understand what the client is all about. The client does share let's say stock images, but of course, because those are not quantified, we can't really tell which is preferred more or which is preferred less. So what's going to happen is that a bunch of, let's say a client has approached us for the design of a residence. So just like using image segmentation over here, using a bunch of stock images and also features which would include what is the style of the particular design on top of, let's say, what percentage of glass is being used, what is the shape of the geometry, etc., etc. Those will be used as featured, and the client will be asked to sort of swipe through the different images and rate which design the client likes by how much, and then using those feedback, the neural network will be trained to basically predict the liking and the disliking of the client. And if, of course, the client goes through enough number of images, then based on that, we can pretty accurately predict a design option would be liked or disliked, at least in terms of aesthetics, would be liked or disliked by the client or not, which basically will take away a lot of time which gets wasted in trying to understand what really the client wants and what the client doesn't want. So again, to revise, we generate a bunch of design options or variants whose parameters are extracted, which are basically called features. In our case, it would be the numericals of the variables. Then the corresponding images or the 3D get reviewed, which basically become the features, sorry, the labels, the output of the algorithm, and then those are used to train a neural network. Now, this will have one more significant contribution, that being its role in participatory urban design. And what do I mean by that? Eventually, for each redevelopment or even for greenfield development of a city, what's going to happen is the particular neighborhood that the design is supposed to be for, the residents of those neighborhoods will be given apps wherein they'll be asked to upload images of precincts or streetscapes which they like, and images of precincts or streetscapes which they do not like. And again, similar to this process, when there's enough amount of data being uploaded by the residents of the particular neighborhood for which the design is, the designer or the design board will learn the preferences and the design sensibility of the residents of that area, and accordingly the design will be informed by that through hardcore quantified directives. So in a way, the design or the aesthetic sensibility that will be preferred by, let's say, people in Beijing will not be the same for people in Singapore or for people in London or for people in New York, right? So through this process, it will not only become participatory, but it will also become bottom up, wherein it will be a significant shift away from, let's say, the idea of the expert telling what should be done and what should not be done, what is right and what is wrong. And instead, we'll have a bottom-up participatory data collection process through which, quite literally, the residents will be stakeholders in the design beyond what is being done now, which is arranging meetings to take their feedback. The feedback will be used to make the design instead of the feedback being used to modify the design. Right. So to the last part of this presentation, let's basically discuss how neural networks work. Of course, people say, or it is said, that it's a bunch of neurons which are connected in a network, which is basically why it's called neural network, of course, right? So it has three kinds of layers. Number one being the input layer, which takes all the features, and the last layer being the output layer, which takes all the labels. And then there are hidden layers, which basically are used to propagate data from the input layer to, let's say, the first hidden layer, then the second and third, fourth, however many hidden layers we have, and then ultimately to the last output layer. How many hidden layers are to be used? We'll get into that later. Let's take this as an example, wherein a neural network is to be trained to identify or classify between a square, a circle, and a triangle. So the output layer would have the labels of course, the square, the circle, and the triangle. Those are the three possibilities. And for a bunch of input data, the neural network is supposed to guess which one of the three is actually the right answer. In this particular example, it's an example of classification, but you'll get the drift of how it works for numbers as well. So let's say we are talking about an image which is basically a circle, and if we zoom into the circle enough, let's say it is made up of 28 by 28 pixels, which is basically a total of 784 pixels. So in this particular case, there are 784 variables or 784 features, right? In the case of absolute tar, there were 12 variables for the definition of the tar. So in that case, the neural network would need 12 neurons in the first layer. In this case, because there are 784 pixels, it needs from 1, 2, 3, 4 or up till 784 neurons in the input layer. So the number of neurons that you'll have in the input layer will be exactly the same as the number of variables you have. Remember, just because it's an image doesn't mean that the image itself becomes an input. Each pixel of the image goes in as a separate input. So once we pass the pixel values, which let's say in this case would be absence or presence of color, it's a 0 or a 1, or in grayscale it would be from 0 to 255. Let's say the data is passed into the input layer of neurons, and as I mentioned earlier, neurons are basically functions. Neural networks are basically a collection of mathematical functions collected and connected in a very smart manner so as to mimic real world applications. Between the input layer and the first layer of hidden layers, these connections have certain weightages, which are in the first step or in the first iteration completely random. So one could have a value of 100, the other could have a value of 0, depending on the domain of the exercise. And these input values are multiplied by these weightages and then moved on to the next set of neurons or functions. Also, there's another, let's say, control, which is that along with weightages to the input, there's also something called bias, which is basically similar to the equation of a line, which is y equal to x multiplied by m plus c. C is the constant, m is another constant, x is of course the other variable. So here each input is multiplied by a weightage, which is similar to m, and then a bias is added to them, which is similar to c. And then those are passed on to the next layer of neurons. However, there is a trick, or there is a catch, which is not all the multiplied and by weightage and then added by bias values are passed to the next neurons. Each neuron is connected to an activation function, which basically decides if that particular neuron is to be activated or not, which is similar to how, again, neurons work in the human body, which is when the electric signal is sent in our body, unless it is beyond a certain threshold, it doesn't get passed to the next neuron, right? The electric signal needs to be of a significant value so that it gets communicated to the next neuron. Similarly, there's something called activation function that takes care of it. So three things are happening right now. Number one, the input value is being multiplied by a weightage and added by a bias value, which is called bias, which is a constant basically. And then once those are passed to the next layer of neurons, each of those next layer of neurons have some sort of activation function which determine if the value that's coming inside it is high enough for it to get activated and then it to be passed to the next layer. And when it's passed to the next layer, the same process happens. This value is then multiplied by another weightage, added by another bias, and the next layer of neurons have again the same set of activation functions wherein they decide if those neurons are to pass on the value or not. Of course, depending on the weightage or the input value, same neuron can be activated for an image and may not be activated for another kind of image. It completely depends on the value of these, of the weightage and the bias and the input pixel value. So let's say in the first iteration of the neural network, through these various combinations, it learns or it predicts that this image is indeed a square. So using the probability distribution of how these weightages are added, it says that 50% chance is that it's a square, 40% chance is that it's a circle, and there's only 10% chance that it's a triangle. This process of multiplying it by weights, adding bias, and finally using activation function to only trigger or make certain neurons work is called forward propagation, where the data or the input is being propagated forward towards the output or the label. Once this is done, because remember, we also have the actual output data with us. If I go back to this, along with all the features, while training, we also have the actual labels for the actual output. Similarly, in this case as well, the data will have the actual output saying that no, it should actually be a circle. As is tabulated here, it should actually be 0, 1, and 0, the probability distribution. Then the neural network calculates the error, which is in this particular example 0.5 plus 6 and minus 0.5 plus 0.6 and minus 0.1. And then depending on this error, it basically calculates how far or how close it is to the actual result. And then through back propagation, depending on how much error we have, it readjusts the weights. So while it was 0.8, 0.2, 0.1 in the earlier case, now becomes, let's say, 0.9, 0.7, 0.3, 0.1. And this keeps on happening again and again and again and again. And this error gets reduced. Remember, the error never becomes zero. Neural networks are never 100% accurate. And there's always, of course, some sort of error. But through this back propagation and forward propagation, where forward propagation is this movement of data here, and back propagation is the calculation of the error, and then recalibration of the weights. Through this forward and back propagation, this process happens again and again and again, till a point where we reach a satisfactory level of accuracy, or till a point where the number of iterations are exhausted. So again, to revise, we have a bunch of input, or in other words, features, which in the case of absolute tau would be variables x1 to x12. Those get fed into the artificial neural network, and there are target values, which in our case would be the originality score, which are basically labels. And then through weight adjustment and error calculation, which is also called loss function, and this process of back propagation through which the weights are readjusted is basically called the optimizer function. Through this combination, it goes through it again and again and again, where randomly it calculates a weight to begin with, then the error is calculated at the end, then the weights are adjusted. Again, the error is calculated, weights are adjusted. So error calculation, weight adjustment, error calculation, weight adjustment. Loss function, which takes care of error calculation, and optimizer function, which takes care of weight adjustment. This keeps on happening again and again and again, like I mentioned, till the time we reach satisfactory results. Of course, the architecture of the neural network can be of various kinds. For example, there could be just one layer hidden, there could be multiple hidden layers. The number of neurons in the hidden layers could be different. The number of neurons within different hidden layers could be different, etc., etc. So it's how are these calculated? These are basically, for each problem, various connections are tried, and then the one which works the best is picked out for use. When we're doing it for the purpose of research or for the purpose of our workshop, optimizing the neural network beyond a certain point is not the aim. When these are to be deployed commercially, that is when an additional algorithm is used to optimize the architecture of the neural network. The thumb rule that we need to remember right now is that the number of neurons in the input layer should be the number of features or the number of variables, and the number of neurons in the output layer should be the number of output or the number of classification, which in the case of our originality score exercise would be just one neuron. If they were to be classified, then it would be the number of classifications in that particular exercise. As has already been communicated to you, we are going to use Google Colab. Some of you have used it, but some of you haven't. The advantage of using Google Colab compared to other platforms which can be used to experiment with machine learning like Paperspace or Runway is that Google Colab is completely free. It uses Jupyter, which is basically web-based notebooks which can execute code, and it connects Jupyter coding platform to its own GPUs, which are basically used to train and then run a neural network. And it provides the GPUs to us for free, which is at least for the introductory or the beginner level of understanding neural networks, is the perfect platform, because the rest of the platforms charge fees. So when you're learning your trade, which is when you make a lot of mistakes, a lot of the models do not make sense, don't really want to be paying for those cases, which is why, again, Google Colab is the perfect platform for introductory cases. What it also has is a very exhaustive set of libraries which are sort of fine-tuned for not only machine learning algorithms, but like TensorFlow libraries, but also for very complex neural network applications like Keras library. Then there are other libraries which are used to plot graphs, upload data, etc., etc. So because it's open source, because it's free, of course, developers across the world are adding more and more, let's say, features to this platform, whereas the other platforms which I mentioned, Runway ML and Paperspace, because it's very rigid, because it's rather top down, it doesn't have as many libraries, and also it's not free. So we're going to stick to Google Colab. What we're going to do today is that I've shared two pre-existing data set with you. We're going to use those to train a neural network to predict the price of housing in Boston. I'm going to demonstrate that, and then I'll give you some time to execute the same with the data in the California housing price Excel. And tomorrow we're going to use Grasshopper to work on the absolute TAR, where we're going to generate different design variants, note down their features, and then rate the design variants, and then train the artificial neural network to predict the originality or the plagiarism score of the new design variants. Keep in mind that this method, this framework, can be used to replace the business of originality with any other score, or rather any other subjective evaluation or opinion. Which opinion you want to use for exercises later on is restricted quite possibly by your imagination. It could be, like I discussed, urban safety. It could be, let's say, you making a design, and one feature could be how traditional it looks or how non-traditional it looks. It basically depends on how you want to frame the problem. Right. That's about it as far as the presentation is concerned. Right. There were some questions. Right. So, Carlos, sustainability, if you want, of course, you can, of course, sort of use that to train a neural network. But remember, because we need the output data beforehand to train a neural network, instead of what we're used to in terms of sustainability, which is run simulations on the machine, what will be suitable to be used in neural networks would be to let's say, map predicted simulated output, as the input. So take the simulated values predicted and then map that to observed values, wherein the observed values would be the output. So those kind of combinations would be useful. And if you're only sort of restricted to predicting the behavior through simulation, which we do through various software, then mimicking that in neural network will not really be so useful. Only in cases of outputs which are not clearly defined, we don't know the delta between the predicted and the observed cases. So those kind of cases would be best. Yes. Right. Yeah, I think the comments are pretty self-evident. That I kind of second what they've mentioned. Any questions? Any further questions? You may not use the chat. You can directly unmute yourself and go ahead with the question.
I had one question.
Yeah, sure.
If you could elaborate a bit further about so the activation function, is it random or what is it based on?
No, activation function is not random. There are a bunch of presets, so to speak, which act as activation functions. Typically, each layer of neurons can have a different activation function, but we don't use it. In supervised learning examples, in supervised learning with numericals, the activation function typically used is restricted to 3 or 4 different types, which we'll cover in the Google Colab notebook. We do not generally vary the activation function types. What gets varied is from within the neural network, it varies the weightages and bias. And as far as we are concerned, we typically vary the number of neurons within different layers, and of course the number of layers, those two values. Activation function and optimizer function, as well as loss function, these have some thumb rules which people tend to use. Of course, there's a world beyond thumb rules as well, where the outlier cases exist. And of course, there are PhDs and researchers into developing new kinds of functions for these as well. But of course, that is not the topic of this workshop. And quite frankly, I will not be able to answer questions of that detail. Right. So what I'm going to do is I'm going to take a break of 5 minutes, and then we're going to head over to Google Colab and work with Excel and Google Colab, and then try and see how the neural network can be trained.